Welcome, students. We are in Chapter 3, Section 2. So we are studying derivatives. And yesterday we explored this new terminology, derivative, and the new notation, f prime of a. And we worked with it in the context of just some additional practice, evaluating the slope of a tangent line or the instantaneous velocity using this limit as h approaches 0 of f of a plus h minus f of a all over h. So what we're going to do today is we have been looking at using this formula to evaluate at a, where a represents a fixed number. But we know that when we evaluate at a, we wind up with a nice little formula that represents the first derivative, represents the slope of the tangent line, represents the instantaneous velocity. And once we have a formula, we can use that and apply it for any a value, which a is equivalent to x, which is equivalent to time. So we might want to find the derivative when x is 1, the derivative when x is 2, the derivative when x is 3. So what we're looking at now today is, instead of thinking of this function as f prime of a, we're going to let the number a vary. Instead of a being a fixed number, we're going to think of a as something that can change. So we are going to replace it with the variable x instead. So slight change to our derivative formula. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. And basically what we're going to wind up doing is creating a new function from an original function. So we'll have a function that represents maybe the behavior of an object, and now we create a new function that could represent the velocity of the object, or could represent the slope of the tangent line at any given value of x. So if we look at example number 1, today's focus is all going to be about not finding the algebraic function, since we looked at that yesterday, and we'll look at that again in the next section. Today we're going to look at finding the function graphically. So the question says the graph of function f is given in the figure. Use it to sketch a graph of the derivative f prime of x. So we want to graph the derivative of this function. Well, we know that the derivative is the slope of the tangent line. Okay, so I'm still going to be working with x, and I'm still going to be working with a y-axis, but this new y-axis I am now going to call, now you could call it y prime, that's a notation for the derivative. If you wanted to stick with the f prime of x notation that we saw just above, you could do that. But basically the y-axis is now going to represent the slope of the tangent line. So what I like to do when I am sketching a graph of a derivative is I like to start by considering what my derivative actually looks like. And it's the slope of the tangent line. So I want you to imagine a little tangent line here, 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 as I work my way around the function. What type of tangent line slopes do I have to begin with? I have negative tangent line slopes. But right down at the bottom, right here, my tangent line is actually going to be horizontal, which would be a slope of 0. And as I continue on, if I were to draw a tangent line here, and here, and here, and here, what do all of these lines have in common? They all have positive slopes. But just when I get to the top of that function, I see yet again another horizontal tangent line. We know the slope of a horizontal line is 0. And then as we keep on going, you can draw more tangent lines in if you like. All of these tangent lines in this interval here are going to be negative slopes. So negative, 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 until we get to the very bottom, another horizontal tangent line where I have a slope of 0. And this last stretch over here is going to be, once again, all positive slopes. Okay, so my goal is to sketch the derivative. So I need to sketch what these slopes out. Now, all of these negative slopes, I know that these are getting flatter, and then they get steeper and then a little bit flatter. I could crank out a ruler and actually manually calculate what I think the slope is, but we're not going to try to be that accurate because we really can't be that accurate. So I'm going to start with what I know with absolute certainty, and that is that at the bottom of this little curve, I have a slope of 0. So I'm actually going to draw y prime in blue here. So this slope being 0 means that for an x value, I am now graphing y prime. Or for an x value, I am now graphing slope. So if I'm talking about an x value giving me a 0 slope, that is a point that is going to sit right on your x-axis if the y-coordinate is 0. Keep on going till you get to the next point where we have a slope of 0. Same deal. I know at this point, whatever x value this is, it's a little bit after 1, my y value would be 0, so I know it would also have an x-intercept. Keep on going. Down here where my slope is 0, at this x value, my slope is 0, so that would be the point, whatever that x value is, 0. So I know these 3 points with absolute certainty. The rest of this sketch is going to be an estimate, an approximation. So yours might look a little different from mine. Ours might look a little different from your neighbors. So there's some steps listed underneath here. The first thing says how to sketch the graph of a derivative. Find horizontal lines because they have slopes of 0. And slopes of 0 graph as intercepts, x-intercepts. So x comma 0 for your slope. Second step, are the tangent line slopes positive or negative? Well, if this is a negative slope, all of these points have some kind of negative slope. Now this one looks a little steeper than this one down here. If you're considering the actual tangent line, that is a lot steeper than that line right here. So I know that when I talk about the x value, something negative, the y value would be negative. So where does a point lie on a graph? If the y value is negative, it lies below the x-axis. So all of these points, their slopes of their tangent lines are all going to be negative, so they're all going to be below the axis. Now, how far below the axis is this graph going to look like this? Is this graph going to look like this? We won't know the exact curvature, but the one thing I do know is that this slope is steeper than this one. So steeper would mean more negative, which would mean further down. So maybe it looks something like this. Maybe all of those slopes look something like that. And I'll sketch this in as a continuous curve in a little bit. So I know that as we get closer to 0, the lines get flatter, flatter, flatter. So this is going to get closer and closer to 0. Now between these two 0 slopes, I know all of these points have slopes of tangent lines that are positive. They actually start to get steeper. Right around in here, I would say, is the steepest, and then they start to get flatter. So I know all of those points are going to be somewhere up here. And I need to start at 0, and I get steeper, and end at 0. So I wind up getting flatter, meaning closer to 0. So what I like to use kind of as a gauge of where exactly to draw all of these points, the most steep point, which I think might be somewhere right around here, is where the greatest positive slope would be sitting. Because remember, for each x value, we're now saying there is a positive slope, which means since I'm graphing slope, a value that has a y value that's positive would be above the axis. And I'm going to graph my steepest point as my highest point. So I think each of these slopes might look something like that. And then I now have an interval where all of these tangent lines have negative slopes. Where do I think it's the most steep? Maybe right around here. So if these all have negative slopes, these points are going to be below the axis where y values are negative. And the steepest point I think is down here. So I'm thinking maybe it's going to do something like that. So I'm going to connect these. Now I'm going to make this as smooth a curve as possible. And then for this last stretch over here where we have lots of positive slopes, these are going to get steeper and steeper and steeper, and the steepest point I think is going to be way out here. Most steep means most positive. So I'm looking at points like this where I have an x value, and then the positive slope means the points are going to be above the axis. I don't know exactly what they're going to look like, but I know that they get steeper, which means more positive. So maybe this graph starts to look like this. And my highest slope is going to be at the very end out here. Okay, so for your steps, for step 2, are the tangent line slopes positive or negative? If it is positive, it is a point that is going to graph above the x-axis because you're looking at a point with an x value and a positive slope or a positive y value. If it is a negative slope on the tangent line, we're going to graph it below the x-axis. So we have x with a negative number underneath, with a negative number for your y value, which means that we are going to be looking at points below the x-axis. And then I like to use step 3 kind of as a helpful tool to figure out how far up or down they go. So where are the slopes the steepest? Those wind up becoming the highest points and the lowest points. So they become the maxes and the mins of your graph of your derivative f prime of x. Okay, so the last part is probably the part that you're going to have the most trouble with, which is what happens when you have weird stuff happening. What do I mean by weird stuff? Well, this graph was a nice smooth polynomial. We will all get very good at sketching what we think the derivative of a polynomial looks like. But what happens when we have sharp turns? Well, you'll find out very soon because we're about to talk about sharp turns. When a sharp turn happens, for example, if you had something like this on a graph, the tangent line right here does not exist. Why is that? Well, a tangent line is coming from this idea of a limit, and this is a calculation for slope. So this is the limit of a slope. And in order for a limit to exist, it needs to approach the same number from both sides. Well, if I am calculating slope, the slope on this side is going to be very steep positive. The slope on this side is going to be very steep negative. The slope at that point is not approaching the same number from the left as it is from the right. So there is actually no point. So a sharp turn has a point that is undefined on the graph of f prime of x. That could look like an open circle. It also could look like vertical asymptotes. And then the last set of weird stuff would be if you have a vertical tangent line or an asymptote. So an example of that might be, let's say you have something that looks like this. Okay, so I'm looking at my tangent lines here. And these are negative tangent lines, negative tangent lines, negative tangent lines. And what if this gets so steep? Now, not vertical, not completely vertical, because it's not a function, it's still a function. So we don't have more than one point where this is the same x value, two y values. But maybe there is a point right in here where the tangent line becomes vertical. Well, if I'm graphing slopes, I would have started with a slope of 0, negative slopes throughout this entire interval. But if right here that slope is very steep and positive, very steep means the slope is getting larger and larger. And well, actually, we're talking about negative numbers. So So smaller and smaller and smaller and smaller, meaning -10, -1,000, -1,000,000. It gets so steep if you have a function that starts to approach -1,000,000, your slope starts to approach -infinity, which means on the graph, it might graph as a vertical asymptote. On f prime of x. And if your original graph had a vertical asymptote, same deal. A vertical asymptote on a graph will sketch as a vertical asymptote on the graph of f prime of x. So just to kind of clarify, on the next page, I'm not going to go through these notes because this is actually what you're doing for homework. This is a printout of your homework assignment, which is on your calendar. This is actually on page 144. So you have a night of homework that is numbers 4 through 12. This is 4 through 12. And so you're going to see some strange problems down here. You know, you've got nice, smooth polynomials. We love those. And then you're going to see some wackadoodle ones like 11, 9, 10, 11, and 12. And that's where you're going to see some points that might be sharp turns, which don't have a sketch of a point on its derivative, or you might see some vertical tangent lines like right in here, or you might see a vertical tangent line in here, which will sketch as a vertical asymptote. Okay, so there's one last thing that we're going to look at in chapter 3.2, and it is the differentiability of a function. And this is really getting into one of the identifiers of these weird points that we might see on a graph. So what are you looking for on a graph that would tell you that a function is not differentiable? Now the first table, first box up at the top, is actually just a variety of notations. So you've now seen f prime of x, you've seen me write y prime. This means the rate of change of y with respect to x. This is the rate of change of your function with respect to x. This is the derivative with respect to x of f of x. And these are just other notations. What are we going to use most often in here? We love f prime of x. We love y prime. And then we'll use dy dx. And that's usually about it. Occasionally we'll see this one, but not very often. So in definition number 3, it says a function f is differentiable at a if f prime of a exists. It is differentiable on an open interval from a to b, or from a to infinity, or -infinity to a, or -infinity to infinity, if it is differentiable at every number in the interval. So when is a function not differentiable? When you have a corner, which I'm also going to call a sharp turn, and that is because f prime of a, or f prime of x, represents a limit, and at this point right here, the slope of the left side and the slope of the right side are not approaching the same number. They are very negative. That's a very positive slope. That's a very negative slope. Look at the second example. If you have any kind of discontinuity, and we know discontinuities can happen 3 ways. The first way is a jump. So that is the example of what we're looking at here. The second way is a removable discontinuity. So that's like a hole. And the third way is an infinite discontinuity. So that is a vertical asymptote. And the very last scenario is probably one of the trickiest to recognize. It's a vertical tangent line. And sometimes it's hard to see that. So once we learn how to find these algebraically, these points of non-differentiability, that will confirm if, in fact, a graph is not obvious enough for you to see that there's a vertical tangent line in there. So there's an example number 4. At what numbers is the graph discontinuous and why? So that's from the last section. So discontinuous, we know at -2, this graph is discontinuous. And around -2, this is definitely an asymptotic behavior. So that is an infinite discontinuity. I'm looking for breaks in the graph, remember. So the next break in the graph is happening at x equals 2, and that is a removable discontinuity. And those are our only discontinuities. Last part to the question says, at what numbers is the graph not differentiable? So we know that one of the occasions where it's not differentiable is a discontinuity. So both of these two will fall under here. So x equals -2 and x equals 2. And what's the reason? Because it is a discontinuous function at those two values. And then the other things I'm looking for are a corner, a sharp turn. So I'm looking for anything with a sharp turn, and I'm seeing a sharp turn right at x equals -1. Sharp turn, corner, whatever you want to call it. Sometimes people call this a cusp also. And the last thing I'm looking for is a vertical tangent line. And I'm thinking right in here at 0, we might have a vertical tangent line in there. Again, we'll learn how to find that algebraically later. Okay, so this is going to be a good stopping point. The next page in your notes has a couple of examples. I'm going to skip over those. Those are just for us to practice in class. So thank you so much for listening. We've now finished section 3.2. And what is coming up next is probably going to be one of your favorite lessons, 3.3, which is our power function. Thank you so much for listening.